Hey guys, welcome back to the YouTube channel of Auditech. Today we are going to discuss about a very serious topic, which is a revolution in today's generation. Today we are going to discuss about quantum computing. So first of all, what is quantum computing? Quantum computing is a rapidly emerging technology that harness the laws of quantum mechanics to solve problems too complex for classic computers. Today, quantum makes real quantum hardware a tool scientists only began to imagine 3 decades ago, available to hundreds of thousands of developers. Our engineers deliver ever more powerful superconducting quantum processors at regular intervals alongside crucial advances in software and quantum classical or resters. So next is, why do we need quantum computers? When scientists and engineers encounter difficult problems, they turn to supercomputers. These are very large classic computers, often with thousands of classical CPU and GPU cores capable of running very large calculations and advanced artificial intelligence. However, even supercomputers are binary code based mechanics reliant on 20th century transistor technology. They struggle to solve certain kind of problems. If a supercomputer gets stumped, that's probably because the big classical machine was asked to solve a problem with a high degree of complexity. When classical computers fail, it's often due to complexity. Complex problems are problems with lots of variables interacting in complicated ways. Modeling the behavior of individual atoms in a molecule is a complex problem because of all the different electrons interacting with one another. Identifying subtle patterns of fraud in financial transactions or new physics is a super collider are also complex problems. These are also complex problems that we do not know how to solve with classical computers at any scale. So, where are quantum computers used? Quantum computers used in many cities, advanced electric vehicles, in many challenging ways. ExxonMobil tries to solve complex energy challenges. Sirens working to explain cosmic mysteries. Quantum computers are used to solve complex problems that are not solved by any regular computers that we use to for gaming and other things. But these are at high level computers. These are high level computers. So next is why quantum computers are faster. Let's look at an example that shows how quantum computers can succeed where classical computers fail. A classical computer might be great at difficult tasks like sorting through a big database of molecules, but it will struggle to solve more complex problems like simulating how those molecules behave. Today, for the most part, if scientists want to know how a molecule will behave, they have to synthesize it and experiment with it in the real world. If they want to know how a side track would impact its behavior, they usually need to synthesize the new version and run their experiment all over again. This is an expensive, time-consuming process that impedes progress in fields as diverse as medicine and semiconductor design. A classical supercomputer might try to simulate molecule behavior with brute force, leveraging its many processes to explore every possible way every part of the molecule might behave. But as it moves past the simplest, most straightforward molecule available, the supercomputer stalls. No computer have the working memory to handle all the possible permutations of molecular behavior using any known methods. Quantum algorithms take a new approach to these sort of complex problems, creating multidimensional computational spaces. This turns out to be a much more efficient way of solving complex problems like chemical simulation. We do not have a good way to create these computational spaces with classical computers, which limits their usefulness without quantum computation. Industrial chemists are already exploring ways to integrate quantum methods into their work. This is just one example. Energy in engineering firms, financial institutions, global shipping companies, among others, are also exploring use case where quantum computers could solve important problems in their field. Quantum computers, an explosion of benefits from quantum research and development is taking shape on the horizon. As quantum hardware scales and quantum algorithms advance, many big important problems like molecular simulation should find solutions. So next is, how do quantum computer works? And quantum processor is a wafer not much bigger than the one found in a laptop. And a quantum hardware system is about the size of a car, made up mostly of cooling systems to keep the superconducting processor at its ultra cold operational temperatures. So superconductors. Your desktop computer likely use a fan to get cold enough to work. Our quantum processors need to be very cold, about 100th of a degree above absolute zero, to avoid decoherence or retain their quantum states. To achieve this, we use supercooled superfluids at these ultra low temperatures. Certain materials exhibit an important quantum mechanical effect. Electrons move through with them without resistance. This makes them superconductors. When electrons pass through superconductors, they match up, forming copper pairs. These pairs can carry a charge, cross behaviors, or insulators through a process known as quantum tunneling. Two superconductors placed on either side of an insulator from a Josephson junction control. Quantum computers use Josephson junctions as superconducting qubits. By firing microwave photons at these qubits, we can control their behavior and get them to hold, change, and read out individual units of quantum information. Superposition. A qubit itself isn't very useful, but it can perform an important trick, placing the quantum information it holds into a state of superposition, which represents a combination of all possible configurations of the qubit. Groups of qubits in superposition can create complex, multidimensional computational specs. Complex problems can be represented in a ways in three specs, making quantum computer useful. Right now, IBM Quantum leads the world into computing hardware and software. Today, a great deal of the work in the quantum in the field of quantum computing is devoted to realizing error correction, a technique that would enable noise-free quantum computation on very large quantum computers. Recent work from IBM and elsewhere have shown that noisy quantum computers may be able to do useful work in the near future. Even before the advent of error correction, using techniques known as error mitigation, IBM has spent years advancing the software that will be necessary to do that useful work. We introduced the Qiskit Quantum SDK. It is open source, Python based, and by far the most widely used quantum SDK in the world. Useful for executions both on IBM's fleet of superconducting quantum computers and on systems that use alternative technologies like ions trapped in magnetic fields. We developed Qiskit Runtime, the most powerful quantum programming model in the world. Achieving quantum advantage will require new methods of suppressing errors, increasing speed, and orchestrating quantum and classic resource. The foundations of that work are being laid today in Qiskit Runtime by IBM and our partner industry, academia, and startups. So, quantum computers are the future. As today, artificial intelligence is running like hell, and everything that quantum computers do in just seconds, that other computers do like in 10 minutes or 15 minutes, a quantum computers do in seconds, or you can say that in milliseconds. So today we have discussed about quantum computers. Hope so you like the video. Please subscribe to the channel and share it with your friends, so they know about the information of quantum computers. That's all. Thank you for watching.